Considering this question, we are asked to use variation of parameter to solve the differential equation d square y dx squared plus dy dx equals to sec cube x. The only thing we can just do from this extent is we believe that d square y dx squared can also be written as y prime prime plus y prime equals the function we have here. This is a non-homogeneous differential equation. Now, considering this part, we need to find the auxiliary equation. That is, we have our auxiliary equation to be, in this case, that should be m squared plus m, then equals to 0. That will be our auxiliary equation. So after that, we can easily factor out m to have m plus 1 equals to 0. And eventually, we should have our m to be equals to 0 and m to be equals to minus 1. Hence, I can then say that then the complementary solution, y complement of x, we believe that y complement of x will always be written as a constant k1, or you use any of your suitable alphabets. You can make use of a and b. So I have a constant 1. In the case of having exponential raised to the power of the m1 I got here, and m2, let's call this m1 and let's call this m2. So I should have my m1 of x and plus another constant to m2 of x. K1 is the first constant, and I have my m1 to be 0x, and that's 0, plus k2 exponential of minus x, since m2 is minus 1. So eventually we should have our k1 plus k2 e minus x. So this is why our complementary solution of x from the differential equation given. So we believe that we should have our complementary solution as k1 y1 of x, and we should have our k2 y2 of x. So by comparing, I noticed that there can be a 1 here whereby y1 is our 1 and y2 becomes our exponential raised to the power of minus x. So since we agree that y1 of x is equals to 1 and y2 of x is equals to exponential raised to the power of minus x, then to use variation of parameter to solve this differential equation we have here, there's a particular formula we need to make use of. And the formula is a very, very long one, whereby we can just decide to say that our final solution, which is y of x, is equals to a complementary solution. A complementary solution plus the particular solution. Plus the particular what? Solution. What does this imply? It implies that I should have my yc of x plus my yp of x. Hence, we believe that from the proof of theorem of variation of parameters, after the proving, we actually have a generalized formula to be given as those y of x to be equals to constant 1, and we have the y1 of x, we have plus constant 2 with y2 of x. Do you believe that this is actually related to what we call the complementary solution of our differential equation? So, and then plus, by severe calculation or by severe proving, we believe that the particular solution of any differential equation from variation of parameter, the expression is given as thus. That is, we should have plus integral of y1x, y2 of x times f of x divided by the root square of y1 of x and y2 of x. So considering this, we know that we integrate it with respect to x. And finally, we should have another subtraction. All these things I'm actually writing is for particular solution. So minus, then we should have an integral of y1 of x also times y2 of x times f of x divided by the same root square of y1 of x, y2 of x, then with respect to dx. So all this is for the particular solution, and whatever we have there is for the complementary solution. So we can go ahead to substitute. Since we already know what our y1 is, y1 of x is 1, y2 of x is exponential. So consider this, since we already know what y1 is and what y2 is, our f of x is sec cube of x. Take note, where f of x is sec cube of x. So on substituting, we should have y of x to be equals to our constant 1 times y1 of x is the constant 1 plus k2 remain as our constant, and y2 is exponential of minus x plus integral of y1 of x is 1, y2 of x is exponential of minus x, then times the function given to us for the homogeneous equation, and that is sec cube of x, all divided by the root square. The root square of y1 of x, y2 of x is the determinant of what we have here, and also by differentiating it. By the time I differentiate this, I should have 0 minus exponential minus x, then dx, followed by the negative sign of y1 of x remain as 1 and y2 of x remain as exponential minus x. So I should have exponential minus x times the same function of sec cube of x divided by the same root square of y1 of x and y2 of x. So on differentiating, I have 0 minus this. So considering this, by the time we solve this out, we should have our final answer in a very easy way. So to solve the determinant for this, we should have this multiplying this, and that should be negative e minus x. So that's what I'm going to have here also, e minus x.